Uh, Welcome back, participants and sir. Can you start the session 4,
Yes,
sir?
I'm ready.
Okay, okay, sir. So, participants, we are starting session 4. Please enjoy the session, and if you're having any query, raise your hand. We will uh, be making options so that you can ask queries to sir. Thank you all.
Can you see the screen, please?
Yes, sir, it's visible.
Okay. Can you see the screen? The title is CPU memory cache.
Yeah, yes, sir.
Oh, perfect.
Video and audio both are okay.
Okay, perfect. So let us start again. So I was talking about um, different country thinks in a different way. So nothing wrong. Every country plays their strategies in a different way, and we should be, contributing to national goals, and that is why we feel privileged to be part of NSM. Now, here is a scientific fact. If you look at this particular graph from 1975 to somewhere 2005 till 2005, there was no increase in the number of the cores on a processor. Okay. However, the performance was increasing. The frequency were increasing, and the sequential performances on the processor itself was also increasing. But somewhere in 2005, everything became flat almost. It started flattening. The reason is here on this particular part of the graph. The amount of power that you are going to give to our processors is limited by power wall phenomena of the microprocessor chip, which means that if you pump more power, it will dissipate that power instead of doing calculations. So it will basically dissipates it as a heat. That means you cannot increase, and it is a fundamental physical fact. It comes from the physics. And the density of the number of the transistors on processor was too high, and there was a lot of interference was happening. If you pump more power, instead of doing calculation, it was generating noise. It was physically not possible. And then the world started to think about the multicore. And once the multicore thought came in, immediately it started pick up. And then you see the number of the transistors again is going on as it is. We all are aware of Moore's law. Moore's law actually played well till 2005 on a single processor, and there was a assumptions that now the Moore's law will die. Now Moore's law took another form because of multi-core phenomena, and right now it is still continuing. The Moore's law is still relevant, but again in 2020, standing 2024 time, people are talking about the end of Moore's law in different way, because the processor itself, the generic processor itself is slowly going away. More and more accelerators are coming up. So Moore's law is somehow, not becoming so relevant, not remaining so relevant in future. That is what people are assuming on. I'm nobody to speculate on, but that is how the study becoming apparent on. What this picture says, it says that there was a significant time in 2005 when all the architecture, HPC architecture of a system, that means the processors more specifically, became single core to multi-core. And that transitions, because of the transitions, there was a lot of different kind of programming technique changes also happened. I will be talking about thread programming. There you will understand. Certainly, from before 2020, 2005, multi-process programs were very important, which is called multi-process programming, is called MPI, message passing interface. And post 2005, suddenly thread programming become more valuable. Why? Because now you do not need to transfer the data from one process to another process, because the process itself are sitting, multiple processes sitting itself on your processor, on your platform, on your server board. There are multiple cores. They are independent processors. So we could launch multiple threads very comfortably on a platform. That the shift happened. That is why the hybrid programming become more prominent. Instead of having normal sequential C type of a program, hybrid programming become too prominent in HPC. This is about cache memories, Udesky. Also in 2010, 2005, that shift happened in 2010. There are two major revolutions was happening around. The first one is accelerator programming was coming up. NVIDIA started delivering CUDA devices. The graphics processors, GPUs become GPUs, general purpose graphics processing units. They become, and at the same time, the revolutions of big data started to happen. For the first time in the history of human civilizations, there was too much of data available to the people. And the people had the capacity also to process them because of Hadoop computing. So, for the first time, they realized now we can mine data properly, comfortably to make sense out of the data. So this is another thing. And then drastically the storage, this is the third revolutions was happening, but well, not much significant. People didn't talk about it much. Drastically reducing the cost of storage. It is humongous things. If you want to store a lot of data, you have to have storage, and for that storage you cannot spend a lot of money. You require cheap storage which is less costly, easy to manage, and things like that. And you see in 2000, in between 2005 2000 to 2005, lot of technological revolutions came since, and eventually we had cloud in 2009 to 2011 era, which enabled to store humongous data on cloud platform. All this propagated the revolutions in HPC as well, including cloud. As I said, HPC, now I'm giving you the formal definitions of it. It is an aggregations of multiple node together in order to increase the aggregate compute power in form of flops, floating point operations per second. And in general, teraflop means 12. So 10 to the power 12 is the most basic yardstick nowadays. If you don't have a that capacity compute power, you don't call them supercomputer, but the definition is dynamic, because you remember in 1961 I was talking about some gigaflop only, 1.9 gigaflop. So giga is 10 to the power 6. So gigaflop operations, here we are talking about multi teraflop systems. So the definition is changing, but in abstract form, it is the same things. We don't consider million instructions per second, which is also a yardstick to benchmark a system's capacity. But in HPC, we do it through flop, floating point operation per second. Now, question is, how do you calculate a flop? Here is a very simple formula. For a single socket, if you have multiple cores on a socket, okay, and then the clock speed, and then flops per cycle. Now, where you can get these informations, clock speed, in most cases you read about in the manual, the systems manual or the process manuals. The thing that you may know or may not know is this: flops per cycle. For that, you have to, if it is Intel processors, you have to go to Intel website, or you have to study a little bit of that, whether it is 8 or whether it is 32. What it means? It means in a single clock cycles, how many fused floating point double precisions, addition and multiplications it could do. Okay. In many cases, it is 8. In nowadays, it is 16. In many cases, it is 8. In nowadays, it is 16. But for some processor, it is 32 as well. Intel many core processor, that is called mic. Okay, Intel many core processor, that mic processors has the capabilities to support 32 as well. So this formula, in order to get the total flop operations capacity, flop capacity of your laptop, you simply have to little bit study about the processor architecture and specifications and bring out what is the capacity of your laptop as well. I've talked about Moore's law, so I would skip. So I've talked about this. Yes, this is important. I was talking about the Indian Institute of Tropical Meteorology. They are hosting. This is old data, by the way. 2019. They are hosting during that time the most powerful supercomputer called Proteus, which is just beside our current campus, just walkable distance from here, the office that I'm sitting in. So the Param Proteus is a Cray delivered supercomputer, Cray XC40. It has 3,763 teraflop R max, and R peak is 4,000 teraflop. So you can say 4 petaflop as well. Okay, instead of 4,000 teraflop, you can say 4 petaflop, 10 to the power 15. So what is difference, or what is meaning by R max and R peak? So when you are constructing a computing system and HPC facilities, you have a theoretical peak capacities. That means you can calculate by looking at the manual of Intel, the processor provider, the processor vendor, and you calculate, okay, I wish to build a 4 teraflop, petaflop system. If I would wish to build a 4 petaflop system, how many nodes, how many compute power, how many racks, what is the total space, what is the civil area, what is the DC capacities? DC means data center capacities, which means cooling, power, water supply, this and that. All I'll touch upon all these areas. So all this planning is required. So you want to build a 4 petaflop systems. Instead of that, what you actually get is 3,700. Why this loss? Because in reality, when some calculations are happening, you measure a system, accumulated system as a whole. Okay, when you are building upon this figure, you are basically looking at the specifications and doing the calculations. This processor gives this much teraflop, this processor gives this much teraflop, so on and so forth. So total becomes 4,000 petaflop, 4 petaflop. But in reality, it is different. How do you measure this? When this teraflop is we are talking about, there is a benchmark called LeanPack benchmark. LeanPack, linear algebra operations benchmark, developed by very famous, very popular, kind of a superstar of supercomputing called Jack Dongara. He developed this benchmark, LeanPack benchmark, which simply does very simple operations: double precision, general, matrix operations, DGEMM. Okay, double precision, general, matrix operations. The operations is like y is equal to ax plus b, as simple as that. So that calculations in a humongous form, in a massive form, is the benchmark itself. So if you run a lean type benchmark, it will tell you what is the total capacity that you are actually receiving in reality. Enough of lean pack benchmark now. Based on lean pack benchmark, top 500 is published. That is why it is very important. Now this is very important. Free lunch is over. This is the end of Moore's law. Actually, it is talking about. It says that now you cannot increase the number of transistors on a processor, so better go for multi-core processors. And when this happens, immediately a lot of things happens around the technological on architecture level. Superscalar processor came. If you remember, in 2005-6, hyper threading came in. Okay, super pipelining becomes standard, branch predictions become standard, out of order executions, thread computations become standard. This all happens because of the reason I was talking about. The whole domain of processing and computing shifted from single core to multi-core. Now it is possible to have a lot of things inside a processor itself, and that is why multi-threading becomes a de facto standard. Eventually, in 2010 and 2012 time, um, uh, the image net dataset as well as the ResNet model, I suppose ResNet 50 only, came up. Okay, so during that time, lot of CNN models, neural network models, also making their entry into the systems. What these models does, they are basically different neural network layers. When there are multiple layers, you would be calling them as deep neural networks. All these networks are doing convolutions. What convolution means? In digital signal processing, convolution means mixing one signal with other. But in matrix operations, what it means? It means doing some operations between two matrices. It's as simple as that. So whatever you are looking at is matrix operations, and that That is the time when graph-based matrix operations came in, because during that time, and before that only, they have been working on. I remember in 2009 and 10, there was no talk of TensorFlow, but a framework called Theano. Theano was very popular, and still it is very popular, very much used for AI processing. But eventually, TensorFlow becomes very popular by after 2009 onwards. What it does, it's a graph oriented flow based computing where uh, large matrix calculations or small matrix calculations is represented as a state, different state, and also the outcomes is given in the form of nodes in the graph itself. So when it happens, all these calculations here in this sections, calculations now can happen on CPU, but they were offloaded to GPU because they are very compute intensive also. That's the reason. That's the reason if you see till 2010-11, Nvidia was doing good. They were not exceptionally good. But once this neural network came into prominence, Nvidia as a company become very powerful. They right now standing on 2024, they are actually overtaking Intel. So that is reason because Nvidia has invested a lot of money behind something called SIMD architectures, single instruction multiple data architecture. By these particular slides, I'm simply trying to tell that how many connections, how many executions, how many operations are involved into deep neural network, and how neural network actually became one of the major candidate on a HPC platform. So my team, in fact, is responsible to avail neural network frameworks on all NSM systems, and we do it through a Linux command called module. If you say module level, what it simply says that what are the different programming or library module available on the system, show it to me. Module level, module list is if you want to actually find out what are the different variations of that. If you want to load, so on a supercomputing platform, suppose there are 20 variations of GCC itself. Okay, 20 different version of GCC. You may not have realized this on a single desktop. On a single desktop, there is only one version of compiler. But on an HPC platform, there can be 20 different versions. Now, which one you want to choose for your calculations, for your executions? You have to decide. How do you do that? You say module load GCC something something. Here you see module load Git, module load CMAS, module load Open LDP. These are basically libraries. Module load GCC, something like that. If you do that, automatically that particular module becomes available to you for your calculations and for your executions. You can do module load also. So how we basically availed, we during that time we took a lot of steps to avail the Jupyter notebook through Jupyter Hub on HPC platform also. For that purpose, SSH, passwordless SSH and SSH tunneling was also very much required, because HPC system is a shared system where at a time there are 200, 300 people logged in, and they are working, they are firing their jobs. They're firing their jobs mean they are executing their programs. So it is a multi-stage jump. First, you have to log into login node. From there, it will be coming to master node. From there, you will be firing the job. The jobs will get executed on compute node. So it's not a very ready-made platform for a Jupyter Hub or Jupyter Notebook, because you understand you are standing on login node, but your job is getting executed on this platform. Then where you are going to run the Jupyter Notebook? So for these purposes, for debugging purposes, for development purposes, we had to adopt the Jupyter Hub, and through Jupyter Hub, through Jupyter tunneling methods, we have built Jupyter Notebook. Another very prominent thing that we decided during that time, I'm talking about 2015-16 time, that distributed deep learning is the very prominent area. And in fact, in India, a lot of researchers are working on it. You have a large model or small model, but you have a limited compute capacity. If you have limited compute capacity, can you actually take help of HPC facilities or cloud facilities to run your applications in a distributed mode? For that, lot of frameworks came up. Deep speed is one such. Hoverboard is a very prominent one. PyTorch Lightning, Determined is very prominent one. So they came up with a distributed deep learning model, and you will be very happy to know that all these models used some of the framework which was very popular already on HPC arena. So HPC scientists, HPC developers, HPC domain users are already using them. For as an example, Horobot is based on MPI, message passing interface, which is a de facto standard of communications between multiple nodes. I will be showing you one example of that. Deep speed, TensorFlow distribute, those modules are also used some of the other protocol which was already is in use on HPC platform. So now I have talked about what HPC is, how different candidates, new candidates are becoming enabled on HPC platform. Now I'll be talking about what are the programming techniques, methodologies that's available. Parallel programming, it is a distributed platform, so we are going to do parallel programming. So what are the parallel programming models are available on the platform? I'll go little bit fast because we may you know go over time. So this is Amdahl's law. What it simply telling in story form, that even if you have a very prominent sections of your code to be parallelizable, but if you have a sequential part of the code dominating on your applications, you may not get good speed up. Actually, you will not get good speed up. That is what it is simply saying. What is actually required? You require a code or an applications which is 90% parallelizable, 95% parallelizable. Then you would get speed up. Otherwise, you see, after certain point of a time, speed up is getting flattened. Even if you are increasing the number of the processor, you are not getting speed up. So that is why a thought process change is required on HPC platform if you are working on HPC. If you are planning that, okay, tomorrow I will be taking up my research and I will be utilizing HPC platform, then you need to rethink again. As I was thinking talking about the quantum computing domain also, you require to orient your mind to quantum kind of a programming. Similarly, on HPC system, you require to orient, redesign, rethink how to parallelize your code, how to design, write parallel codes. In most cases, people are not habituated and parallel programs with parallel programs. Designing a parallel program, thinking about a parallel program is not difficult. Debugging a parallel program, delivering the correct result is the challenge because it is a distributed platform. So that is why multiple different approaches are there to guide you, to tell you that if you want to develop a parallel application, please select one of the approaches so that eventually you do not fall into much of the difficulties later point of a time. So like while you are developing an applications, it is good that you select an object oriented methodology in order to develop a clean, readable, nice applications, modifiable later point of a time easily. In a similar fashion, if you want to develop parallel applications, please follow these some of the methodologies. They are not very difficult to understand, and that's why I would go fast. In case of master and slave, it's very simple that one master node. Here I'll be talking about node and process interchangeably. So because when a process is getting executed, it is mapped to some node on hardware, right? So that's why sometime I'll be calling node, sometime process. So the master process, one of the process is responsible to distribute the task to multiple other process, and those process is actually mapped to different processor or nodes. So that means these arrows are basically describing you how the data is communicated over the network. And that's why it is important that stage wise you receive the task from the master, then you compute the task and give back the final result. Somewhere in the computational flow, the master is responsible to join back, collect all the data, join back, and make sense out of it before they go beyond this scope of executions. That means before they move forward. There is another method. It's called distributed distributions model or phase parallel model, where the task is distributed. Here, the task is of similar kind, but the data is different. Okay, so you may say, what is the difference between this and this? Not much difference, but the access mechanism of the data is little bit different. So also one point you must look into that here there is no master process. All processors are basically slave process or compute process. So somebody amongst them would be distributing the data. All of them will compute on their own respective data, and somewhere they will gather the data. This model sometimes can be called as scatter and gather. That means somebody is scattering the data, scattering the task workload, and then after the computations it will be gathered back. Another model is called data pipelining. This is very popular and easy to understand. Sorry for the mistake, it's going out because of some animations. So in case of data pipelining, I suppose whoever is student of computer architecture, they knows that data pipelining is at place at the level of architecture also, where it simply means that one task will be done by one entity and the other task will be done by other entity, and they will be working in pipeline. If you look into a single flow, they will look sequential, but if there is a multiple flow, you will see the throughput, higher throughput. Okay, it is as if like one person is putting the letter inside envelope, then the other person is sticking it, the other person is stamping it. If they do one after another, it looks sequential, but if you have multiple such pipelines, the throughput, overall output throughput would be very, very high. This is called data pipelining model. This is very popular, called divide and conquer. And I suppose in data structure, all of us have studied this. You have a humongous problem, humongous challenge, humongous computational task at your hand. You want to divide it into multiple subtasks, and then the subtask will be divided into further subtasks, and it will be eventually mapped to some processor for calculation purpose, and the final results will be gathered back in opposite or reverse fashion, kind of a tree structure. Divide and conquer problems is everywhere, and at designing of parallel program and parallel programming applications, this is also required. One common thing is very necessary is called decompositions. I have talked about it, so would not take much time. It simply means that how do you decompose your data, how do you decompose your calculations is very, very important, because these smaller blocks, you see the smaller blocks, okay, are, let's say, decomposed form of workload. Sometimes it is a workload, sometimes it is data. You can think of interchangeably. So if they are decomposed like this, and what this arrow is meaning, they are communicating with each other. So this particular node, can someone confirm if they are able to see the pointer also on the screen? Because I'm moving the pointer, the mouse pointer I'm talking about. Madam, can you confirm?
Hello.
Yes.
Uh, Sir, this
Yes.
is visible.
Okay. So these connections between the dots is basically the communications pattern. So that means if this particular dot is sitting on processor number 1, and if this particular dot is sitting on the processor number 100, and there will be multiple hops between them. Though here it is a single array, a single arrow or single connections, in reality on a computing systems, reaching from node number 1 to node number 100 is a multiple hop. It's a network communications protocol. To avoid them, you need to decompose the data in such a way that the this data and calculation workload sits on process number 1, this sits on nearby process, let's say process number 2, etc., and etc. which means that the way you are going to decompose and thereafter the way it will be mapped onto physical system, it has a lot of impact on to overall performance of the system. And that is why energy hour mapping, where location wise mapping of processors in parallel programming is itself is a domain of research. There are a lot of algorithms underplay inside the framework which will take care of it by itself. But if you are a student, you are thinking of higher studies, you can think of this kind of a problem statement where 2D mapping, 3D mapping are happening also. And also network protocol plays a major role there. Functional decomposition simply says you have a lot of work, different type of different modules. If you can module wise divide the task and if they can go parallelly. So this is as simple as that, function wise decompositions. So through these particular sections of explanations, I am trying to simply tell you when you will be devising and then designing and developing a parallel program applications. In case you do that, you have to look into system organizations, how HPC nodes are connected with each other. You need to have a little idea of it. Also, you need to understand the system architectures, how it is going to give me the performance. If you are not looking into it, then you will not get good performance. You have an jet engine, but you won't run in jet speed. Okay, that's the fact, where a performance engineering role, like mind role, comes into play. We tells the domain scientist, okay, your applications is this, and then you need to modify these parameters or this way or that way. You need to apply these set of flags in order to tell the compiler or the runtime that the organizations of the system is like this. Then it will give better performances. And that's why we belong to a team called benchmarking team. Now I'll move into called system organizations. As I said, once you understand different methodologies of designing a parallel applications, you need to understand organizations of the system, how it looks, how it is connected, how they are placed. I will be delving into that page. Is there any questions in between? Okay,
I think there is no question.
I suppose no questions. Okay, let us move ahead. Here is a basic organizations. Now I'm not talking about architectures of a processor. I'm talking about how systems are placed, organized, and that is why it is called HPC cluster organizations. How they are placed. This is a schematic diagram just to tell you that these are the set of the components are there. Initially, as an end user, you'll be logging into somewhere here by using SSH command. Once you log in into here, you'll be dropped. Either you will be remaining here or you will be dropped to something called execution node, compilations node. Okay. However, in many cases, the login node itself is a compilations node. Okay. However, in you possibly would not go here. Okay, you will not be drafted here. Who will be drafted here? The system administrations. They are responsible for managing this particular node. Head node is the cerebral unit, the main brain of the whole cluster. It keeps account of everything, all the resources, the state of the resources, the challenges of the resources. If some node is down, it will take account of it, also display it to you. So once you log in here, you will be firing some command to ask what are the set of the nodes are available for your computation purpose. It will also look into the state of the resource, storage, etc. Now, even if there is a head node and these are the set of the compute nodes, there is a special storage server. Why it is required? Because I was talking about, if this particular node requires some data from here, it starts to receive the data through it, then there will be a lot of bottleneck, because it may happen many other processes are also trying to retrieve the data from here. And that's why in between another component came in to manage all this access parallelly. It's called storage server node. The storage server node keeps alive a parallel file system. Also, it keeps multiple data. It's take responsibility of a replications of data across, and then it makes the data available in minimal possible time, the fastest way possible. So that is what the main purpose of this. Now they are all hardware, all right. This is the network which is connecting all of them. This is also hardware. These are all hardwares. These are all hardwares. Which thing? What is the thing which makes them alive? The software, the software layer. Now the operating systems cannot do that itself, because you see, operating systems, there is a operating system instance here, there is a operating system instance here, and all the nodes are also having their own operating system. So there are multiple operating systems running. So there is another abstract layer comes in, which is called middle layer, where there will be another meta scheduler called meta scheduler called resource manager. There will be a process manager. There will be middleware manager. Middleware manager would be responsible for managing the runtimes. There will be a lot of user applications, and also monitoring tools, debugging tools, compilation tools, etc. All of these, if they are working in sync, then only in harmony, if they are working on, then only we would be calling it is an operational cluster. Though semantically it looks like this, practically it is like this. The important part to note is, you see here multiple connections are given in different colors. IPI management network is responsible to manage. So the facility, I'll show you the design of a HPC facility, where mostly the engineers, the system administrations would not go inside the facility because it is supremely cooled. It is not allowed to go inside all the time. If there is a hardware failure, then they will go. In other cases, they will be using IPMI protocol, which is remote based protocol to manage the complete system. They can manage everything, including shutdown. Even if some component is shut down, they can reboot it also by accessing this network, and that is why it is called management network. Using this, they can boot up, boot down, they can rearrange, they can redesign the whole network also, because nowadays it is SDN kind of a thing. Then there is something called gigabit Ethernet. Why this gigabit Ethernet? Because it is less costly. So the users, which is, let's say, some of the users after logging in wants to directly log into onto this compute node. Now this is not a compute node. Here it is a compute, because it only require one single system, and it wish to use the systems as a independent node. Okay, like their desktop system, like their server system. If that is the case, they will not be given high speed network access. So the access, the remote access, the authentication mechanisms, many other access mechanisms happens through gigabit Ethernet. It's low cost. Whereas the InfiniBand network, which is fiber optics based networks, that means the communications happens through light. That particular network is a high speed. If some computations is happening and then it wants data from the storage, it will use the InfiniBand network. InfiniBand network is very costly. InfiniBand switches are equally costly. So that is why we have multiple network fiber, or we call backbone fiber, in order to connect the systems in a different way. This also gives the possibilities for any reason any of the network is down, we have little bit chances of recovering them. The other important part is here, you can see there can be multiple rack, and the J boards are basically the storage bay. That means on a single bay you can see multiple storage hard disk, which is basically SATA disk. Lot of SATA disk are plugged in. They are hot pluggable. Anytime you can plug out, plug in. The server unit, the storage server, which is storage one here, is responsible to keep a replica of the data which is suddenly taken out, and ensure that some of the calculations do not fail. If it fails, there will be a lot of journaling mechanisms and data backup mechanisms taking place automatically in the systems. So this is kind of a thing. You have a monitor here. By any chance, if any engineer wish to go and directly access the systems, they go here, directly open up the monitor and then start working upon. Also, in many cases, for many of the systems, you would see a visualization server. Visualization servers are responsible for visualizing the end data or executions data. The back side of the systems looks something like this. This is Paramjuba picture, and also you could see a lot of fans here, which is responsible for cooling. I'll be talking about what we could see here. A lot of wires and connections. Here also you could see those are basically the cooling related mechanisms in place. I'll be talking about them. Now here is a software middleware part of it. What are there on the system? When I say on the systems, you would ask whether this whole thing on compute node or on the head node or on the login node, where it is. So the answer to this is all of the systems, all of the nodes will be having this. All of the nodes will be having this. But some of the nodes will be having the compilation capacities. Some of the nodes will be having the what do you say, daemons, only daemons running of these applications on compute nodes. Also, there are a lot of other tools like C-Chaksu, which is developed by CDAC, CREAM, which is again developed by CDAC, lot of automation script and things. So this is the complete stack of the whole systems, but it is not that all of the nodes, compute nodes will be hosting all of this stack. It may happen compute node will have only two layers and some of the daemons of C-Chaksu, whereas head node will be having the compilation facilities and things, lot many things. Login node only will be having this. They would not be requiring the other things. I'm just speculating because login node also have some portions of Slum. So I'm just giving you an example that multiple type of nodes will have multiple software layers available with them. However, the basic OS part of it is common across. Same version of OS is also required for HPC facilities, which is not strong requirement of a cloud computing. We are moving to Alma Linux. Earlier it was CentOS based, CentOS Linux. Right now we are moving to Alma Linux based systems. Now you may ask whether we do everything manually. No, we don't do, because there is something called XCAT, which is again cloud related software, which automatize all this work, aggregating, connecting, validating, booting, shutting down, managing all the compute nodes, storage servers, and the software stack automatically. And that is what the primary purpose of XCAT. I will go a little bit fast here. So at the lowest level, at the granular level, lot of network related services works on every node. There is a serving node, there is a compute node, and you could see that DNS, NTPD, syslog, D, they are everywhere almost. Okay, so these are the daemons which is continuously running on the systems to give feedback, which we normally call as heartbeat back to the management node, main head node. Because if those heartbeats are there coming properly from different compute nodes, then we will say that the compute node is alive. And for that purposes, all these network protocols, different type of databases are in place. Different kind of protocols are also used. So what is the basic workflow in normal sense? Initially, if you ask XCAT will start discovering the resources, whether some node is properly working or not. Once it finds out that yes, all the daemons are responding properly, and it can find all the heartbeats properly, the log informations properly, it will say, okay, the node is healthy, and then it will consider it under its resource pool, and slowly it will do it for all the nodes parallelly, so that it happens fast, because there are, suppose, let's say 10,000 nodes in big supercomputing facilities. It is true there are multiple thousand of nodes. So if that is the case, to boot up, it will take 1 day if you go sequentially, even more than that. It doesn't happen that way. It happens very fast. It happens parallelly. Once the boot portion is completed, XCAT is confident enough that everything is fine, then it will start processing informations. It will give the interface to different compute node. Nowadays, there is something called PXE boot facilities. So what is happening in a compute facilities, you do not actually install the operating systems natively on that compute node. When you ask some compute nodes, suppose the compute node is not available, it's down, then on the run on that particular compute node, XCAT will install the OS, create a complete ecosystems on that compute node, and make it available to you if that compute node is healthy enough. So this is also is there, which is called PXE boot or runtime booting of the system. That is how lot of energy is saved. Suppose during night time all the nodes are not required, or some holidays are going on, so XCAT will take care of these. The slum, there is a resource manager also, it will consider whether there are 1,000 nodes can be shut down or not, because it will save a hell lot of energy. There comes the resource manager's part. Slum, simple Linux utility and resource manager. Slum is a very popular tool. It also keeps monitoring what are the resources available. XCAT is responsible for organizing and building the whole cluster. Slum is responsible for looking after the healthy cluster status. So everything happens through Slum. You do not directly submit a job. You submit it through Slum. You give a command to Slum and tell him that please take this task, execute it on the systems. Then Slum will do that. How Slum it does? It runs a lot of daemons across different systems and checks the heartbeat of the systems as well. It is of similar nature. So all the compute nodes will be having, there is something called Slum daemon. Okay. So also the controller daemons will also be there, which you're looking into and things like that. Slum is also responsible for scheduling the jobs. Scheduling means suppose there are 200 users and they are submitting the jobs. They are actually submitting the job for the execution purpose. Slum is responsible to ensure that none of the jobs is submitted to the compute nodes immediately, directly. It must go through Slum itself. Okay, that is the first purpose. The second is once you submit it, it will also take care of the job itself. You submit the job, go home. After 3 days, you come back, you will find the results properly. So that is the methods in a shared system in a HPC facility it works. Because some of the jobs run for 1 month, some of the jobs run for 48 hours, some of the jobs run for 1 second. So whom to take care? Who is going to look after? Slum is going to look after. You are not going to look after manually sitting in front of the terminal and day and now and night just to see whether your job is completed or not. No, you submit the job, continue and go on developing your applications and do your research work. Slum will inform you. Even the mail systems, message systems, call systems is available. You will get an email reply telling that your job has not been executed successfully because of this and that error. That facilities are also there on many of the clusters, many of the situations. Otherwise you will get a mail, you will get a message, something that sort of. Scrum uses a mechanism called backfilling, which is very popular, which simply says that if job 1 and 2 is running and you have submitted job 3, job 4 in the queue, if the resource is not available, it will not run the job 4, rather it will try to backfill. Okay, we simply says that when job 1 or job 2 running, job 4 came, but it was also demanding the resources of job 1 and job 2, but it was not available as the job 1 and job 2 was occupying those resources. So the job 4 will wait. In between, if another task comes which require less number of resources, which is right now free, it will come immediately, fill up the portions and it will start executing. Whereas job 3 is continuously executing for longer period of time. This is called backfilling mechanisms, a normal common sense oriented approach. However, there is a scientific study also that backfilling mechanism is very, very powerful, useful, and efficient. All right. So this is what the organization's part of the system. That means till now we have talked about how the system is organized, who is looking after and making a cluster systems as a cluster system. Now I'll go into hardcore performance aspect, the computer architecture part. I'll go fast here because I know many of you have already gone through. I have half an hour to cover the portion. So what it simply does is at computer processor level, earlier it was sequential executions, but latter point of a time, multiple pipeline has came up. The pipeline processors, the pipeline processors are capable of executing multiple instructions, as I was telling, 16 instructions per clock cycles. So that happens because you have superscalar processor. Superscalar processor means superscalar. So it has multiple scalar processing units. Scalar means two integer getting added upon. This is a scalar operations. Another two integer is getting added upon. This is a scalar operation. If there is a possibility that these two operations happen simultaneously, we will be calling them as a superscalar processor. How it works, if you have a pipeline mechanisms or pipeline processor, it will facilitate superscalar bandwidth output. So it will be overlapping of instruction fetch, instruction decode, execute, write back, memory access, whatever. So these cycles continuously works, and if you have multiple such pipelines, then there is a overlapping situations, and in every after these two clock cycles, or from this clock cycle, there is in every clock cycle one execution is happening. Okay, and that is how you are getting higher bandwidth. After there is a super pipeline. What it simply means, even um, in a capacitor phase, a digital circuit cycles can be divided into two phases: charging phase and discharging phase. Okay, a capacitor. That means a digital circuit look like digital cycle clock cycle look like this. Okay, so what they did simply, during the charging phase, the clock cycle during the first phase of the clock cycles one operations, during the second cycles the half portions of the other operations. That is how they have super overlapped, and that is it is called super pipeline. It improves the latency one level. uh, After that, then is superscalar processors. It is another form of multiple pipeline on a single. So if you have two ALU, then you have a superscalar unit, two arithmetic and processing unit, two independent pipeline. Then you have such things. SIMD processor, MIMD processors are those processors. Slowly, from this particular picture, we are delving down into a processor which is high end, server class, and HPC ready. So in a single picture, it looks like this: scalar versus superscalar versus super pipeline. All this technically is helping to get better performance. Then comes something called hyper-threaded processors. What they simply did, it is an Intel technology. It is right now a standard one de facto. There are multiple instructions and their stages are there. If it can be reorganized, rearranged, or mixed upon, in order to ensure that we can rearrange them in such a way that we do not miss a single clock cycle. Okay, so uh, horizontally we look it here. If I can rearrange the task here and somehow channelize it properly, then I will not miss a single clock cycle to do some useful operations. That is how hyperthreading. You have three ALUs here, okay, three ALUs, but it will appear as if you have three cores. You do not have three cores. Here you have three: arithmetic and execution unit, arithmetic and logic unit. But your systems will appear as you have two cores or three cores, multiple cores. You do not have multiple hardware pipeline. You have single hardware pipeline starting from here to here. But it will appear as if that you have multiple pipelines, hardware threads. Now coming to something called vector processing units, it's little bit different. Here you have multiple hardware unit, independent pipeline. You see here, the data is coming through this complete pipeline. Here you have multiple independent pipeline. This type of processor is called vector processor. If you have processor has vector processor, you can see that suppose you have a array where the index wise 0, 1, 2, 3 is supposed to get added with array B 0, 1, 2, 3. Then in a single clock cycles they can be mapped. Suppose and the zeroth cells of array A and B will be added up on this vector processor, and so forth on all other processors. That way, in a single clock cycles, multiple array cells operations would be performed. Then came multi-core processors. In a multi-core processors, the difference is that here the hardware pipeline, which is supposed to reside inside CPU, is not only replicated, again the cache memory is also replicated. That is how it became multi-core, independent processor itself. If you look into this section, this is multiple core. This is a core. This is a core, independent core, whereas they have some level of shared cache memory. All these were happening around 2005, and before that also another development was working upon called coprocessor design. If you have lot of floating point operations, you do not wish to do that on processor, because processor will be blocked. It won't be able to do any other work. It will be overloaded. Can we offload the floating point operations to some coprocessor? That is what the coprocessor design concept. And from there, the modern day GPU processors came in. GPU processor become very prominent coprocessor. It is connected through PCIe slot on the motherboard, and you can offload large number of calculations onto that. There are other parallelization techniques which help on day-to-day basis to do asynchronous calculations called DRAM, double data rate RAM, because it's parallelly allow you to access multiple banks of memory unit on memory itself, DRAM itself. Okay, and there is DMA unit, direct memory access. So asynchronously, when the processor is doing some calculation, floating point operations, if some storage access is required, DMA can do the storage access. CPU do not need to worry. We all know about DMA access. So this is also an asynchronous way of improving the performance. So that way, everywhere there is a lot of aspirations, a lot of initiatives going on around by the processor designers in order to improve the performance of a single or multiple processor. Eventually, we can categorize anatomically the overall parallel computing architectures in single instruction, single data, single instruction, multiple data, multiple instruction, single data, which do not exist. There is a category, but it is not. Theoretically, it is there. We do not see any processor of this kind. And then there is multiple instruction, multiple data. Cerebras or network processor, systolic processor, TPUs, or something in that sort of so multiple instruction, multiple data. There is subcategories under single instruction, multiple data. We have vector processor, array processor, whereas multiple instruction, multiple data, we have grid computing and another CC NUMA, non-uniform memory access processors, etc. And then here is an important part of it called COW, collections of workstations, and that is the cluster systems. So this is actually the anatomical representations of processor as well as a system also, because we are talking about grid systems, hypercube systems, cloud systems, and cow also. If you look into the thread aspect, here is a single thread processor where you can launch limited number of threads, where coprocessors look like this. In case of shared memory, you have multiple CPU, but memory is shared. You have multiple processor in a distributed computing systems. That is also possible here on a, sorry, this is multi-core thing. And here, whenever the internet is coming in, it is loosely coupled. So if you look at this area, it is tightly coupled. If this way, it is loosely coupled. So on the left hand side is one chip parallelism. On the right hand side, it is more of distributed computing, cluster computing, cloud computing, grid computing, etc. All right. So MISD, I think these are all jargons you would be able to go through. I have explained them: single instructions, multiple data, and MPP, multiple process things. This is kind of a grid computing and cloud computing falls into this category. This is cow architectures. All right. What I do on day-to-day basis, this is what our work platform we do, take responsibilities of lot of applications on cluster systems from bioinformatics, molecular dynamics, so on and so forth. There are set of visualizations tools also. These are the set of the visualizations tools. We also provide this set of AIM and DL set of frameworks, technologies like Enroute, and also we evaluate lot of different architecture: Intel, AMD, IBM, NVIDIA, ARM, you name it. We have explored some form of it. Key applications are these, based on which we day-to-day basis works. If you look into architecture diversity at this point of a time, you have x86 CPU, then you have x86 64-bit CPU, you have ARM processor, then on the architecture side you have NVIDIA architecture, which is basically GPU, AMD. Little lot of AI oriented GPU accelerators are coming up like Intel P, FPA, Cell broadband engines. How do you program them? This is so much diverse computer architectures. How do you program them? You have set of computing programming techniques. C++ is the core base, Fortran, C++ and Fortran. But on top of it, you have multiple thread programming model, process programming model, etc. I have another 20 minutes. So, so what I will do, I'll tell you about two very simple programs. Till now, I have talked about too much. And now let us go through one simple program which would be able to call as a parallel program. Okay. I think except this particular line, okay, all of you would be able to read this and understand what it is. Hmm? These are header files inclusions, this is main program in entry point, and then you are simply trying to print hello world. That's it. But you don't understand possibly what is this. Let me decode it for you. Has, anything starts with has, we call it has pragma, is a preprocessor directive. What does it mean? Preprocessor directive means before the computation works, compiler is going to rewrite the code here in these sections. So compiler is going to do something, okay, with these sections of code which is enclosed in bracket, in order to ensure that not a single thread but multiple threads run this program. Okay, when I say multiple threads runs this program, how do you define multiple threads? On command prompt, okay, on the cell, on command prompt. If you are familiar with Linux platform, you basically get access to a cell. So there you have to export a variable called export omp num threads is equal to 4. Then this particular statement will be printed by 4 different threads parallelly. If you want to compile them, it's a just simple GCC compiler. Okay, the program name is, let's say, hello world cpp, and this is the executable name. Okay, but here it is important. You are saying f openmp. This is a flag telling the compiler that I have included something here in my program, which is you need to understand and rewrite the whole code, or possibly these sections of the code, in such a way that 4 threads will be executing it, and I want them to be getting executed parallelly, and you give me the output. So you are basically telling the compiler this by this flag, and then flag, when compiler will be running this program during runtime, it will check how this is a runtime variable. So during the runtime, it will check, okay, there is 4, so that means I have to run this program by 4 threads, and here you see the 4 threads. But one thing to note is the output. They are not sequential. It is not 0 1 2 3, because you do not have control on the threads. Whichever threads got the processor mapping first to do its execution has printed the output first. So that is what the beauty of it, also the challenge of it. Beauty means all the threads once start getting executed are independent. You don't have control on them. They are parallel, but the output is jumbled enough, so you have to be a little bit patient to read them whether they are correct or not. Now this is a multi-thread programming paradigm. I require actually a lot of other more time to explain many things around, but time is very limited here. So in fact, this is 20 years of my life I'm summarizing in 2 hours, something like that, 2 hours or 3 hours. So here this is a multi-process programming. What it simply does, if you read, you will be able to read it. There is one header file called mpi.h. MPI stands for Message Passing Interface. You understand this, but you don't understand what is this two and what is this two. Okay, this one. Let me decode it for you. MPI init, it's simply telling this is a multi-process. That means it's a distributed programming. I don't know how many of you have run socket server client socket programming, uh, client server model programming, socket programming you did, network programming you did, but here it is everything is done through MPI. You don't have to do it when you run it. Okay, I'll show you the command how to run. This is important. I'm running it. I do not simply say dot slash send receive. I'm simply saying MPI minus n 2 dot slash send receive. It simply means MPI is the runtime to whom I'm telling run my program, this process with two process. This particular executable will be ran, will be executed by two process. Okay, at the same time, where those two processes will be executed, they may get executed on single node or they may get mapped to different nodes. Please remember the network protocol I was talking about. So it is possible that processes are running on different nodes or on single nodes, because here is a loosely coupled model. So process and processor is a hardware term, process is a software term. So process based on mapping protocol may get mapped onto single multiple process as per the situations. Now what it does, I'm now here you see there are two parameters, ARGC and ARGB. What I'm simply telling by this, I'm initiating an MPI world. You see here MPI com world. What does it mean? By this particular command, I'm initiating a communications world where if I use the command that please initiate two process, so that both of the process 0 and process 1 would know that in this world I exist, but along with me my brother process 1 also exists, so they would be able to communicate. So this is what the beauty of it, a virtual world is getting created where every node will be getting its rank by this particular pointer. So this is basically I'm passing a pointer by reference, okay, pointer by address, and on this particular variable which is not assigned here, for process 0 this particular variable will be assigned with 0. For process 1 this particular variable will be assigned with 1. So by this particular state here, by this line, there are two processes running, process 0 and process 1. For each of them respectively, node variable is holding the value 0 and 1 correspondingly. Then if they print the hello world, both of them will print hello world, and they will print their node ID number. This is the node number I'm calling, but it is basically the ID, software ID number. So this ID number for one process it will be 0, for another process it will be 1, and then they will finalize. When I say finalize, it is like the whole creation, the whole world is getting destroyed. So the both of the processes will get destroyed by this particular command. So here is, I call this as a Brahma. This is Vishnu area where it is basically maintenance, and this is Shiva where it is getting destroyed or basically annihilated. So after this executions, there will be no existence of those processor on the system because it has completed its work. How it will be giving the output? Let me check whether I have. Oh, sorry, I have not printed any output here. So this is the idea of it. This is how multi-process programming works. This is how a cluster parallel program works. This is the most standard de facto multi-process programming paradigm, which is called message passing interface. At this point of a time, this is the de facto. Every scientist use it. This is a C program, but there is a Fortran map of this. You can write the same program in Fortran. There is a Python map of it. There is a Java map of it. There is a Julia corresponding of it. Everything, but all of them are MPI, message passing interface. I'll take a pause here if there is any questions, because I may assume that there may be some questions. If it is not, I'll move forward. No problem.
Participants, do you have any questions? Because we are having almost 10 minutes in our hand. So you can ask quickly if you're having any question. You can raise your hand and then we'll unmute your voice.
So
I think so, you
anyway,
continue.
yeah. So anyway, this is what the status is, and then this is another program you may go through because of lack of time. I'm just skipping it, but important part is MPICC. This is the
Sir,
compilation. This is running.
sorry to interrupt you. One participant is there, Orijit.
Yeah,
He's having some query. Yes,
yeah,
also,
yeah, yes.
please.
Yes, sir. Am I audible?
Yes, yes, please.
Yes. So, sir, you have already told that multiprocess communications, but can we actually divide this multiprocess into multi-threaded further?
That's a great question. Actually, you can hybridize. In fact, that is what the purpose is. OpenMP program. This is called OpenMP program.
Yes,
Hmm?
yes.
And this is MPI program.
Mhm.
So both of them can be merged together to develop a hybrid program. So
Okay.
MPI will responsible for spawning the multiple process or multiple node, whereas OpenMP will be responsible for running multiple threads on same processor if you have multiple cores on the processor itself. Okay, so that is
Okay.
the beauty of it, hybrid programs. It's an
Okay.
advanced topic. I have not covered and talked about it, but yes, it is absolutely possible.
Okay. Thank you, sir. Thank you.
Now, this section is GPU computing. I do not have time to go through. I wanted to, but maybe some other time. How CUDA computing or CUDA processor works. These slides will be with you. Please go through it. It's easily understandable. CUDA is a very, very fantastic programming model where for the first time you could design the compute unit itself, computational model itself. That means you can actually design how many threads, how they are designed, etc. Okay. So this section is talking about hybrid programmings. You see here CPU and GPU memory, and then on a single platform you have CPU, GPU accelerators. How do you program them? How do you take benefit of such powerful platform to get maximum performance? These are these are the questions, and the answers is this. You have different programming models available for you. You have to learn them: OpenCL, CUDA, Intel TVV, SQL. Those are different programming paradigms you have to learn. Here it is: MPI, OpenMP, CUDA, OpenCL, etc. If you learn them, you know that yes, it is possible to program and develop programs hybrid mode. This is a single slide telling you a very simple fact that all the domains which are compute intensive domains, financial analysis, physical simulation, etc., they have different kind of kernels, SBM, PDEs, etc., and etc. They belong from two different areas, but the end of the day on a computer systems they fall into two basic categories called basic matrix primitives, basic geometry primitives. So that means there is a lot of solvers. Okay, these solvers are combined together into some libraries sometimes called BLAS, basic linear algebra subroutines. BLAS libraries, C BLAS libraries. Those libraries are very much important. You people need to know if you want to do parallel programming to get performance, maximum performance, because they are developed by scientists, computational scientists, and that is why matrix operations, if you look for, you would never be able to overperform beyond them. They will always give better performance than your matrix operations. So you better use their libraries. Intel MKL math kernel library is one such library. You have BLAS, C BLAS, Atlas. All of those libraries are very popular, and they're open source as well. The beauty of HPC is most of the things is open source. The whole stack is open source. This is C Chaksu, and it is developed by our team. My colleague Sucheta Power has developed, leading the whole development. It gives you almost a runtime monitoring of the whole cluster itself. We have been proposing this open source tool, sorry, not open source, this proprietary tool, and this is available under NSM. and this will become an product eventually under CDAC. All right, so a lot of things. Now let us talk about employment. I used to call it roti kapada makan. We do not know about these technologies much. We have talked about it. Why? But another major factor is employment. Because India was mostly working on the service industries lately, so it was not investing too much time into core scientific computations much. The researchers, the domain scientists used to go outside country. They used to learn distributed computing, parallel computing outside and come back and then continue their research here, accessing remotely the supercomputing facilities of US, Europe, etc. Right now, you have NSM, lot of compute facilities, and scientists are utilizing it. Changes are there. Why we don't see computer science people directly jumping onto it? The major challenge is the course curriculum. Lot of people do not study the computer architecture much, software data structure much, also operating systems detail part of it, especially Unix design of Unix operating systems, the detail part of it. All of them are jumping onto many of them are jumping onto, I would not say all of them. And there is certainly a lot of people are there from IITs, premier institutes, MITs, etc., NITs. So, but mostly there is a lot of interest in the digital domain, digitizations domain, service domain, and nothing wrong. So, however, the whole domain is slowly coming up, and eventually, lot of demand is there. In fact, every second day I get requests from different even people to have expert or rather experience resource in HPC, and we do not have. So that is one thing. You may also take up higher studies. One good thing I would tell to the student who is attending these sessions, if you are thinking of higher studies, if you can attach HPC and distributed computing in your resume, you have higher chances for higher studies outside, higher chances of support and approvals. I can assure you that because many of my students who did internship under me are working in outside countries, US and Europe. So I can certainly say that distributed computing signs up your resume, academic resumes to be very specific. If you are domain scientist, you need to learn HPC for sure. If you are computer people and thinking of doing academic studies and also a career under this, you have to be good at these three subjects. So as I said, okay. So quickly, lot of technologies are coming up to minimize the power consumptions. You could see that liquid cooling technology. So the coolant goes through this and come out through this. During that time, there is a heat sinks mechanisms here. These copper pipelines are basically is to transport the coolant from one end to another end, and eventually they will go to the chillers. So the boxes are here. This is hybrid chillers. That means all other component except the processor is cooled through normal air or normal vapors, cool air, whereas the other the processor part is cooled through coolants. All these coolants will travel to the chillers. Here you see, once it travels to the chillers, there is a portion where the chillers are basically the basically some form of water. It is cooling down. So there are some portions where water in one side of the wall or one side of the metal wall there is water and another side is the coolant. So once coolant touches that metal wall and on the other side there is a cool water, so the heat exchange happens and the coolant becomes cooler than the current temperature, and then they will travel back to the processors in order to cool down. Why we do that? Well, this is cloud computing infrastructure as well as HPC infrastructure common here. Huge amount of power consumption, huge amount of, I'm telling you, cloud facilities or HPC facilities big enough can actually consume the power of a middle level city, what a middle level city consumes. That's why there is a lot of research goes around in minimizing the power consumptions of a facilities. So here is a array of chillers you could see. Um, I have given the links where I have got these pictures from. You please visit them if you are interested. Also, data center related papers, a good read a paper. So this is the data center facilities eventually on day-to-day basis looks like. Now I'm talking about the civil architecture. So while you are planning for it, you need to plan a lot of things: total weight, power consumption, cooling requirement, cooling possibilities, airflow, all these things. uh, this is elevated floor. What happens is cool air is pumped from here and hot air is taken from top. So this is what another mechanisms. Earlier it was very popular, nowadays also it is there for common facilities, not for the processor. For processor it is coolant mechanisms works. So this is how the overall facility design works with. If you look into standard facility, HPC facility, it looks like this. Here inside, most of the time you are restricted, you will not be given access to, whereas you'll be sitting somewhere here, you can see the scientists are working on, you have a lot of visualization access here. This is data centers basically freeze cooling, the whole room cooling. I'm not talking about the cooling the processors. This is backup batteries. If for any chance the power goes off, then here is the generators. The generator would start upon kickstart, but between that time you need to keep running the facilities because a lot of explorations and scientific simulations are going on which cannot be stopped in between. Some of the scientific simulation goes for month, so scientists would go mad if their process get killed in between just because of those facilities getting shut down. So there are a lot of backup mechanisms are working in place. These batteries would actually power the whole facilities for certain period of a time, let's say 15 minutes. Within that time the generators will kick start and then it will empower the facilities. A very quick diagram. How do you use the systems? Here is the mechanisms. You give SSH. This is mobile exam. You use no day-to-day basis SSH username and the IP addresses of or host name. Then you will drop down to some terminal. This is cell I'm talking about. Once you are there, you will be firing a command called sinfo. Okay, info is nothing but you want informations about the cluster's resources. So here you see the slum, the sinfo is a slum command, is telling that compute node number 3 to 4 is in mixed state. That means it is getting utilized partially. Compute node 1 to 8 to 15 is completely allocated. You cannot use them. There are ideal compute nodes. Okay, so you also have these called partitions. So once you log in, you have an authentication mechanism. That means you cannot always access all the partitions. Possibly sometime you may use GPU partitions, you require permission for that. Sometime you will use normal partitions. Suppose you want high memory nodes. In that situation, there will be high memory node partition. You will be using that partitions for firing your job. How do you fire a job? I will show you one Slurm script. Now, again here, I am using a tool, a command called spec, which is telling me what are the list of different version of libraries available
Sir,
once I get
I'm
into the system.
very
Yeah,
sorry to interrupt you.
yeah,
Actually, it's almost time to wrap up.
I am
So
almost done.
very
One more slide.
sorry. Okay, okay, okay.
Yeah. So this is what it is, and then you have submissions of the job. If you want to submit a job, you call it as batch pytest and then test.sh, and then it will be submitted. After some time, you can also check. You will get a job number, okay, and you can cross check whether the job is alive or not or completed or not. The script looks like this. It is basically giving you the capacities to define the partition, how much time it will take. If something goes wrong, here is the Gmail IDs or mail IDs you have to give. The command look like something like this. Once you complete your job, you also need to remove the directories and data, something that sort. And this sections is basically environment. Well, a lot of things to discuss, but yeah, I'm almost done. I have talked about it. I do little bit of quantum simulations, hybrid quantum computing on day-to-day basis. And thank you.
Any questions? I think there is one. Okay, I'll request all the participants to kindly switch on the camera so that we can quickly take few photographs. Participants, please switch on your. Sir, you can stop sharing. I think you have stopped that.
Yeah. Is it okay now?
Yes, yes. Participants, please switch on your camera. Participants, we told you to switch on the camera, not to switch on the audio. Just give us 1-2 more minutes. Okay, parallelly, I think Audijit was having some query. Audijit, you can ask your queries. Somebody call Audijit, and there is Umar
No,
Farooq.
I have no query.
Okay. Then Umar Farooq.
Sir, what exactly these accelerators are doing in HPC space?
Okay. So the compute intensive kernels that I've talked about is basically a lot of array calculations, matrix calculations. So the accelerators are very good for matrix operations, and that is why, and they also consume less power. And so, and also you can plug multiple accelerator on a single node, and that means that with less power consumptions you can do lot many floating point operations on a single processor or on a single node. So that is why nowadays you don't see a normally CPU based HPC system, you see hybrid HPC systems where thousand of accelerators are installed inside the processor itself.
Okay, participants, you can switch off your cameras. Thanks for the cooperations. There is one more participant over there who is having a query. Jinatul. Sir, please ask your query. First, unmute yourself. Jinatul sir, if you are having any query, you can ask. Otherwise, we will end the session for today. So, thank you, sir, for your time, patience, and this wonderful presentation. I think time is very short to share so many things in this 3 hours.
Yeah.
Anyways, sir, definitely we will again contact you for like any sort of this sort of sessions, and of course in offline mode, I think it should be quite better for us. So that's all from our end. I think Jinatul, he's unmuted, but we are not able to hear him.
I think he's speaking up.
Somebody called Prabhu. Uh,
Okay, can you enable the chat box so that they can write the queries?
Sir, one humble submission, sir.
Yes,
Most
yes.
of the when we attend this supercomputing related seminars or this FDP, this coding part they usually skip. But you explained the coding part very clearly, sir. Now it is providing some insights for us on the coding part. So next time we will ask more doubts, sir, because now only I started learning about this coding part, sir.
Oh,
Thank you for your wonderful
thank you.
explanation, sir.
I belong to programmer side, so I know the pain. And I ensured, as I said, it's a very long presentation. I don't want to bore people. I just wanted to give concept. Possibly some other sessions, other time, I'll dip down into parallel programming very specifically because I belong to that domain. I would love to, discuss parallel programming to be specific, design of a parallel programming. In fact, nowadays, a lot of sessions on CUDAs are going on. Computer Unified Device Architecture, NVIDIA CUDA program. So thank you for that feedback.
Thank you, sir. Thank you very much, sir.
Okay, so sir, thank you and good night to you. And
Thank you very
if
much.
it will be kind enough if you kindly share your presentation with us.
At earliest,
Um,
madam, but I was till last moment I was working on the presentation, so I will just review one more time, and tomorrow morning we'll have it for
Sure,
sure.
sure, 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 sir. And I will share with the participants. And along with that, if you share few papers of yours, which will
Okay.
help the participants, or the research scholars are there as well. So it will help them a lot.
I think you have my mail IDs. You may share my mail IDs with people who is interested to discuss with me in case or get
Sure,
in touch. That is also very much welcome.
sure.
And I really appreciate presence of you conducting these sessions, and then your organizations for giving me the chance, and above all the patience of all the participants, 205 I
It's
could see.
almost
So
just 230 plus participants were there throughout the sessions.
yeah,
But
so
credit
so
goes to you also.
I was scared that my sessions would be boring, but somehow they
No,
survived.
no, 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 sir.
So thank you very much. Good night,
Sir, yes, sir. Good night, sir.
and wish you
Uh,
all happy Sankranti. Today is a very special day. I am hoping to get some pithe puli after reaching home.
okay.
So wish you the same. Good day.
Thank you very much, sir. And same to you and same to all the participants. Um, okay, so good night, everyone. Please use your registered mail ID to send the feedback. Otherwise, it's not possible for us to manage everything. There are so many participants. We are using multiple feedback, multiple links to share the feedback. So please, everyone, use your registered mail ID to submit the feedback. It's a humble request from our end. Please use it. Otherwise, it's very tough to handle everything. Thank you, everyone. Thanks for your patience, hearing, and of course, uh, thanks for everything. Okay, so good night. I have shared the link in the WhatsApp group. Um, please check it out. I am mailing that one as well. If any issues are there, we are on. Till 15-20 minutes in the chat section. You can write it to us, or tomorrow morning you can please contact us. Okay, thank you, everyone. Kamala sir,
Madam,
please. Yeah,
madam, one humble submission, madam.
yes.
Madam, attendance will be updated daily, madam, or on a last day, madam.
Sir, this is our planning, so we are not going to disclose this right now, but you think that it is daily manner, so please upload your feedback within 11:59 p.m. every day.
Okay, madam. Okay, madam. Thank you, madam.
Okay, 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 thank you, sir. So Kamala sir, please end the meeting.
Yes, I'm stopping this record and
Yes,
I'm
yes,
closing
yes,
this meeting.
yes, 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 sir. So tomorrow